Groundswell are proud to present Dr. Tom Sheahen. We're fortunate to have Dr. Tom Sheahen here visiting from the United States for discussions with the farming communities about the real science concerning the warming effects of the greenhouse gases. Tom's expertise and qualifications are Bachelor of Science degree, PhD degrees in physics from the Massachusetts Institute of Technology. He is a well-known scientist and presenter on climate issues. He is the chairman of the Science and Environmental Policy Project in the USA and the president of Western Technology and an independent consulting firm specialising in energy technology issues with business implications. After his presentation, there will be time for anyone with genuine and respectful questions. Please, if we can all be respectful and remain quiet until then, please give a warm welcome to Dr. Tom Sheahen.
Well, thanks very much, Brian. It's a delight to be here. And I'm just delighted to see so many of you here. I remarked to Brian before that, gee, this must not be a church meeting because everybody's sitting in the front instead of sitting in the back. So I'm going to talk about why methane, even despite all its publicity, is in fact an irrelevant greenhouse gas. This is not what you've been hearing on media, TV, and so forth, but I'll try to make the science clear, and you'll understand why you as farmers are entitled to, capable of, and well-armed to fight against any taxation based on methane. So we'll begin. Let's see. I got two parts to the talk. First, I'm going to review the work of a couple of people from North America, William Van Weingarten from Canada, and Will Happer from Princeton in New Jersey in the United States. And I'm going to pay particular attention to methane, CH4, and nitrous oxide, N2O. What happened was, after many years of inferior models and clumsy calculations, Van Weingarten and Happer went back to the first principles of physics that govern optical radiation absorption, etc., and radiation transfer, and they got it right. And you're going to see why in a few slides. What happens when I say right is that their calculations agree with satellite data. And that's the measure of success in the world of science. The scientific method is you have data, measurements, perhaps an experiment. But that data rules, that governs, and you have to fix your theory until it agrees. And if your theory doesn't match the data, that theory gets dumped, and you try again, try harder. And what they achieved is exactly that accomplishment. They got agreement between their theory and data, and therefore it becomes possible to believe what they did and work from their results to some important conclusions. Now, the other half of my paper deals with a magical number that is out there in the media, press, literature, the parliament, and every place else. And it's called GWP, or maybe GWP star, or GWP 100. These numbers are all cousins of one another. And it stands for global warming potential. It's an attempt to compare other gases to carbon dioxide. And man, just as Van Weingarten and Happer got it right, the GWP people got it wrong. And I'll show you why that is wrong. So, the bottom line of all of this is you have three major pending policies: to tighten regulations, to put taxes on the ruminants because of their methane, to run up the higher cost for the farmers. And all of them are pointless and unnecessary, and as farmers you ought to be confident that you can fight against it because you've got scientific facts on your side. When you talk about atmospheric radiation, we got to pause for a minute to define a couple of terms. Something is called forcing. This is what you see among the scientists. Forcing has to do with the amount of energy coming in your direction. Forcing refers to radiation that carries energy, and it's usually measured in watts per square meter. The sun constantly bombards the Earth with 340 watts per square meter. Well, at night, when the sun isn't shining on half of the Earth, it responds by radiating away energy. 100 watts per square meter is reflected back into space, right off the atmosphere, off the surface of the ocean, whatever. 239 watts leaves the Earth's atmosphere from infrared cooling radiation. And on the way, there's all kinds of interesting things that happen, where there are collisions between molecules, there's emission of a radiation, there's absorption. It gets pretty complicated, and Van Wijngaarden and Happer took it into account correctly. The IPC has not. And as a result of that, it's been 30-some years that consecutive IPC reports have always made projections and estimates of the future temperature that are wrong, wrong, wrong. And there's no reason why a farming community or a farming nation should cave in to a theory that is wrong. So what happens is this. You have energy coming in from the sun, the yellow input arrow. 51% of it actually makes it to either the ocean or the ground, and then that gets radiated away. But it isn't just radiated away, it's carried away by convection, that is wind gusts and so forth. Water evaporates from the surface of the ocean, gets into the air, goes up to the higher troposphere where it deposits its energy into the gas up there, and what you have is a rather remarkable system of physics that is well balanced and takes energy in from the sun, sends energy out, and ultimately the top of the atmosphere, that is about 80 or 100 kilometers up, radiates away into space. And that's how the planet gets cooler. Think of a simple molecule like O2 or N2, nitrogen or oxygen. Dumbbell type shape, atom here, atom here. All it can do is wiggle back and forth like that. On the other hand, a molecule made up of 3 atoms, like carbon dioxide, nitrous oxide, any of these, has got 3 atoms, and it can wiggle, it can twist around, and do all sorts of things. And so a triatomic molecule or a polyatomic molecule has many more chances to either emit or absorb light. And all of this takes place in the infrared, in the area where the Earth is giving off radiation to cool. There is an important principle I'll just mention in passing, that energy levels are quantized, a result of quantum mechanics. And the only light you can absorb or emit is at certain spectral lines. And that's important when you look at this carefully. A bunch of such lines is termed a band, and a band has a center and it has wings. And the way in which absorption and emission takes place is that the center fills up first and the wings later. The sequence of this taking place goes under the name of saturation. Take a dry sponge and rub it on a damp floor, and you pick up some water. Wait until the sponge gets wet and it doesn't do any good anymore. That's saturation, right? In the atmosphere, with gases like CO2 and H2O, eventually what happens is that it has occupied so many of these energy states that the rest of the energy goes right on through. Radiation goes right on through, even though CO2 and H2O are in the way. And that's called saturation. And it kind of looks like this. You really have to squint at this chart. I wish I could make it bigger in some way. But when you first dribble in a tiny amount of some gas, And this chart has to do with CO2, but all the other gases are the same way. The first 5, 10, 20 parts per million does a high percentage of the absorption. Here, in this case, we see a peak that drops down by 80% in absorption. That's how much is absorbed. 80% of the radiation coming at it is absorbed. That is, only 20% gets through. And that's in the first little bit, the first 20 parts per million. So how can that happen? The air is, you can see through the air. Well, in the infrared, you can't see through the air. And that's an important distinction. The length of the path is about 100 kilometers, and when that's thrown into the mix, it turns out these gases are pretty effective at stopping radiation. Again, going back to this, you see after 20 parts per million, then 40, 60, 80, on out, more and more. Where we are today in the case of carbon dioxide is at 410 parts per million. That's way over there on the right. So, at first, 80% of the energy was lost, then 85, then 88, 90, 92, 94, 96, 96 and a half, 96 and 3/4, 97, da 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 da. And right now, we're at about 98.5%. The only greater amount is another little 1.5%. And you could put all the carbon dioxide in the world out there, and you would have not getting any more absorption, because it's all been done already. From the point of view of the greenhouse effect, H2O and carbon dioxide are the whole story. H2O is 75% of that story, and carbon dioxide is 25%. So no one claims that carbon dioxide doesn't matter, but changes in carbon dioxide from now on don't matter at all. Wrong button. There we go. Okay. The warm Earth emits radiation. So does the ocean surface. Okay? It's called infrared radiation, and in particular, it has a certain shape that goes under the label of black body radiation. That's a term of art used in the field of physical chemistry. The atmosphere emits and absorbs some of this energy. Some, but not all. What happens is this slows down the excursion away from the Earth of heat. You've heard the term traps energy. Well, not quite. It isn't very good at trapping, it just slows it down. And all night long it gets a little cooler, and the Earth is heading for equilibrium. But it doesn't quite get there because about 7 o'clock the next morning the sun comes up and the whole cycle starts over again. But that process of the Earth reaching towards equilibrium is what's driving this entire process of planetary cooling. The greenhouse effect is the difference between blackbody radiation and the actual radiation. In a couple slides I'll show you exactly what that means. It's a little annoying that it doesn't advance like it's supposed to. Okay. Van Weingarten and Happer wrote several papers published in the period between 2019 and 2022, and they calculated the radiation emitted and absorbed by all 5 of the greenhouse gases. Remember, there's 5 greenhouse gases: water, H2O, carbon dioxide, CO2, ozone is O3, methane is CH4, and nitrous oxide is N2O. That's the whole story on greenhouse gases. That's it. Those are the candidates. The model that they used differed from the IPCC in an extremely important characteristic. They considered real air. Now, it takes a minute to explain. When you're doing a laboratory experiment, you don't want any moisture in your gas. It messes things up. It really wrecks your experiment. So you take air from the outside and you run it through a long tube that goes over little pebbles called desiccants, and all the water gets soaked up with the little pebbles, and what goes past you into your apparatus is called dry air. So it still contains CO2, methane, etc., but it doesn't contain any water, and therefore you can do laboratory experiments with it and get decent results that aren't messed up. Well, that's nice for a laboratory. We have a thing called the U.S. Standard Atmosphere, which is agreed to by everybody in the world. It contains no H2O. It's great for a laboratory. But that's what you cannot use in the real world, because the real world contains real air. There's an amazingly important distinction, and the IPCC calculators ignored it. They went ahead, did their calculations based on dry air, and when it was clear their answers weren't right, they said, oh, we better put water in and some patchwork. Wrong, wrong, wrong. Wrong way to go about it. But the difference between dry air and real air is an important distinction, and I'll bet you not 2 people in your entire parliament know that. It just has been gone over the head of almost everybody. There we go. Here's what's different. When you compare individual molecules, carbon dioxide versus CH4, methane, it kind of comes out the same. They absorb infrared radiation, they emit infrared radiation, so you do it in a little laboratory chamber filled with gas, and you get answers for each molecule. They're different within a factor of 5 or 2 or something like that. However, per molecule is not what we're dealing with. We're dealing with an atmosphere that contains 1.5% H2O. Whole different world. They calculated the real atmosphere. I'm sorry to keep hammering on that, but it's so important to realize that real air versus dry air is a huge difference. So H2O is the dominant greenhouse gas. Everybody has agreed on that for a couple centuries. Carbon dioxide is secondary but finite. It accounts for 25%. Ozone has a little notch which takes, ozone absorbs in the stratosphere, and we like that because it keeps the ultraviolet rays from giving you a bad sunburn and maybe a skin cancer. But both the tiny trace gases of methane and nitrous oxide completely vanish when you do a full-scale calculation. What they did was a calculation so good that the theory, their calculation, and the data from satellites are absolutely indistinguishable. That's the proper use of the scientific method. They got it right. The computer model was incredibly detailed, but they ran it. In their abstract, they used the phrase, exceptionally good quantitative agreement with satellite observations. That is, the observations you get when you're looking down from space towards the atmosphere. Okay. Don't be too turned off by this slide because it's terribly important. You have 2 columns of figures and 2 rows, left and right. Over on the right is real data from real satellites. In the left-hand column, matching each paired vision on the right, view on the right, is their calculation. Study those curves for a minute. Look at all those jagged little edges. Every one of them matches perfect. That's what their phrase, exceptionally good quantitative agreement is. They duplicated in a calculation what's going on in the atmosphere. The top pair, left-right, is from the Sahara Desert where there's very little H2O. The next one is, I don't know, Europe or the Mediterranean where there's plenty of H2O. And the third one is from Antarctica. And I don't have time enough to go into the Antarctica one, but it's very, very special. And in all 3 cases, look at left to right, examine all the lumps and bumps, and see that the agreement is perfect. Nobody does this. I've never seen an experiment and a theory that matched this well. They come close, they got wiggles here and there. But to get this kind of agreement is absolutely stunning. It's unprecedented. thing that's supposed to advance. Okay, the major accomplishment that they made in their series of papers is the correct use of the scientific method. You believe the data which you have measured with care, and then you fit your theory to it. I regret to inform you that the IPCC didn't do that with the calculations that have been these grandiose models that have dominated so much of politics and climate change theory for some 30 years. Model that is correct. Then you can trust the predictions made by the model. So they set out to think about or calculate about some imaginary atmospheres. One of them was when there's no CO2. What happens then? Another one when there's no methane. They could do this, and we can believe the results because the certification or guarantee of their quality is that matched real data. I mentioned there at the bottom that we don't have to pay attention to artificially constructed numbers, and later on I'll talk about the global warming potential, which is exactly such a number. Okay, here's a comparison of carbon dioxide. Just briefly, hard to see, but when there is normal CO2 as we have today, you get the black line. When there is no CO2, you get the green line, okay? And when there's double CO2, you get the red line. Can anybody see the difference? Can you see the difference between red and green? You can easily see the green line, right? But let's look at a close-up of this. This is a much better picture to look at, annotated appropriately. The outer envelope, the blue line at the top, is what you would have had if there were no greenhouse gases. That's what a bare planet would look like in radiation. But what you really get is the black line. And in their calculations, they said, let's do it with 0 CO2, and they got the green line. So, when there's no CO2, that great big gully, that ditch, that canyon of absorption isn't there anymore. You have a whole lot more light comes through, radiation comes through, and therefore you wind up with a different planetary radiation budget. But again, we're talking artificial. Now, let's double the CO2. And now get out your magnifying glass and see if you can find the difference between the black line and the red line. Everybody's, oh my God, what will happen if the CO2 doubles? We're all going to die. People carry on wildly. But here's what really happens. This is accurate. This is what's going to happen if CO2 ever doubles. You move from the black line to the red line. And this is important to realize, that these little tiny differences. The reason is because CO2 has already done its damage. It absorbed all the energy it could, can't get any more, so the light's going to keep going right on through. I mentioned that little purple or magenta chunk. That's where ozone takes out some light. Ozone is useful to us because it saves us from the ultraviolet, but ozone plays a small role. And maybe you should know that nitrous oxide is in the very same range as methane. And what's going on is, as you see the difference over in the far right between the outer envelope curve and the black line, that's all due to absorption by water vapor. And that's where methane wishes it could play. But there's only 1.8 parts per million of methane. There's 15,000 parts per million of H2O. And guess who's going to win? You're outnumbered 15,001. You're not going to get much radiation capture. So, I say there in red print, effective doubling CO2 is the difference between the black line and the red line. I've squinted at this 100 times, and I barely know how to find the right spot. And I've had practice. The reason carbon dioxide doesn't do any good when you double it is shown right on this graph of saturation. It all happened in the first few parts per million, up to maybe 100 parts per million. And now that we're out there at say 410 or 420 out in the red. Okay, double it, up to 850 or something. By then, your graph is out there to where the thing says Groundswell NZ over there. And it's flat, flat, flat. Nothing else is going to happen. So go ahead and double CO2 and nothing will happen. And that's a very important point to understand about this whole process of atmospheric radiation and heat transfer. Now, they did the same thing for the case of methane. And here is where uninformed and inattentive bureaucrats, politicians, and others who don't have any scientific competence want to tax you. We have the outer envelope is the blue line as before. The black line is what's real. And now, and you have ozone and carbon dioxide as normal. And when you go over to the right, you can see the green line for CH4 equals methane. Okay? That's what you get when you have zero methane, is the green line over there. When you have regular methane, you get the black line. And when you double methane, as in, oh my God, we're afraid of the sheep and the cattle, you get the red line. Can anybody find that? Yes. Oh, good idea. I'll late for you. Yeah. So there's your green line. That's a whole area. The whole business of methane doing anything to the atmosphere all takes place in this narrow little band. H2O is all over the place. Here, there, there, there. H2O is very active in absorbing the infrared. But methane is this little tiny bit. And if you can find the difference between the black line and the red line, you've got better eyesight than I do. Oh, and by the way, they did this for N2O as well. This is a close-up, an enlargement of that little tiny area that I just focused on a minute ago. Green line, no methane. Black line, 1.8 parts per million, what today's value of methane is. Red line equals methane doubled. Do you want to pay a tax for this? I don't think so. And there's no reason why you should, because the science is on your side. Add more methane, buy twice as many sheep, whatever you want to do, and your absorption curve, the effect on infrared light, the effect on cooling or heating the planet is going to change by the difference between the black line and the red line. Again, if you can even see it, you've got better eyesight than I do. So here's what all these experiments mean. If carbon dioxide were zero, it would make a big difference, about 25%, and the Earth would be cooler. If CO2 is doubled, it would make a very small difference. Remember the CO2 chart where it was very hard to see the difference between red and black? As for CH4, methane and N2O, nitrous oxide, they're extremely hard to find at all on any graph. So they don't contribute to the greenhouse effect. Methane is an irrelevant greenhouse gas. And that's an important message that not only you want to take home, but deliver that message to your legislators, your bureaucrats, and others. And don't back down. If they tell you, oh, gee, Happer's degree is in something called physics, not in climatology. Climatology as a defined field has only been around about 20 years. And the quality of knowledge that these physicists and many others like them have is way beyond a minor distinction like that. Happer is a fellow of the National Academy of Sciences. He's one of the top, most brilliant scientists in the country, and he doesn't have to back down in the face of somebody who maybe went to college and majored in political science and took a minor in climatology. The guy's an eminent scientist, and so is his colleague, Van Weingarten, somewhat younger. But many of us realize, we understand physics and atmospheric radiation heat transfer well enough to know that this is correct science. So you can forget about methane. You can forget about methane doubling. You can forget about methane tripling. It's not going to matter at all. So, remember this. The reason you can believe the Van Weingarten-Happer results is because they got agreement with measurement data. That is what science is all about. You have to get that accomplishment to have your theory agree with your experiment in order for you to be said that your theory is correct. That's how science is supposed to be done. This is so much better than all those complicated models known as general circulation models that the IPCC has been spending big bucks running for the last 30 years. Every 6 years they come out with another report, and every 6 years they keep doing the same computational models with touched up here and there, little tweaks, but still with a very fundamental error of looking at dry air instead of real air. But Van Weingarten and Happer did it right. Now, again, they met the conclusion, a little more CO2 makes a very tiny difference. Nitrous oxide and methane make no difference at all. And I say in my last line, I said, buy twice as many sheep, no sweat. So here's the 3 reasons why methane doesn't get any more important. There isn't very much of it. Less than 2 parts per million, 1.8 currently to be precise. And if you compare CO2, there's 400 times as much. And H2O at 1.5% is 15,000 parts per meter. So if you're not used to this, using the number parts per million, sorry. If you're not used to using letters like ppm, just think about that colossal difference between H2O in the atmosphere and CH4. H2O always wins out in a competition for a stray photon here and there. It's just, it's more. It's just plain more, and it takes away all that radiant energy that methane might have been eligible for. And there's one last thing about it. The amount of energy that the Earth is radiating is rather small in the area where methane can compete. Later in the talk, I'm going to show you a slide that shows all this important bands of methane all over the infrared, but they're in an area where nothing is radiating. If nothing's radiating, there's nothing to absorb, and therefore it doesn't matter. Again, here's our methane comparison. Blue curve at the top is what you would have gotten if there were no greenhouse gases. Black curve is real, and there's the dent there because of CO2, and way over in the right area, around there, is where methane plays a role. And how in the world, from this physical reality, anybody could possibly get the conclusion that methane is a dangerous or worrisome gas just boggles my mind. People who pay attention to science will never make that mistake. So here's your policy implications. 1, you've got a good model. They got it right. Van Weingarten-Happer got it right. That's science, the proper scientific method. You can believe their results, and you can believe what they tell us about the variations of carbon dioxide and other gases. And you don't have to believe what the IPCC's summary for policymakers says. Greenhouse gases are not going to stop the climate from changing. The climate always changes. Therefore, don't take expensive action to mitigate climate change. Don't strive to reduce CO2 or other greenhouse gases. And don't impose new regulation or taxes on farmers. Go to your parliament and stand up for this, because you are right. You're the ones they want to impose this on. You are the ones who will suffer from that bad judgment. And when science is on your side, you don't have to back down for anybody. All right, I got to skip a couple because we don't want to run too long. Quickly, the fundamental error is right there in the top line. Real air is real. Dry air is a specialty laboratory gas for laboratory experiments. The difference between them makes all the difference in the world. And always remember that there is a greenhouse effect, and H2O, water, is 75% of the game. That's the main one. Fundamental error also was that they tried to correct for the absence of water via a feedback mechanism. And it was mistaken. It didn't work. And it kept making mistakes, and it made the IPCC calculations wrong again and again and again across many models and across many years. What happens about feedback, by the way, is very simple. A feedback mechanism does change the signal, is an electrical engineering term, but nature contains feedback mechanisms, and they always tend to bring the system back towards equilibrium. So if you have a little more ocean evaporation, and therefore a little more water in the air, and therefore, that's going to converge and come back to equilibrium. It's not going to run away. This planet has been around for 4.5 billion years, and it's never run away. There are no tipping points, and things come back to normal. All right, now I've got to talk to you, the second part of the talk, about why that magical number called global warming potential is useless, wrong, nonsense, etc. So GWP stands for global warming potential. There's GWP 100, etc. In AR4, if any of you were to read it, the computational method is described there, pages 210 to 214. And the intent was to try to get a ratio that this gas is so much worse than CO2, or maybe not as bad as CO2. And we're going to do this for a whole lot of gases. The only ones they needed to do it for was methane, CH4, and nitrous oxide, but they did it for a whole bunch of gases. So they put in all these simplifying assumptions, and they skipped a lot of details, and they presented this big, fancy table of data. The real purpose of that, folks, is to snow you, to leave everybody impressed. Say, oh boy, what great calculations. This is from the IPCC. It must be right. And they desperately hoped that no one would read it. Well, they were right. No politician, no bureaucrat ever read this stuff. The only guys who read it are us, who are their critics. Here's the first mistake leading to GWP. Here's the whole infrared, okay? Whole infrared range running from a very low frequency up to a frequency of about 1,000 wave numbers, which equals 1 micron. You see bands there for the various chemicals. Water absorbs over here. Methane, great big absorption peak there. What's this? CO2, CO, NO, more H2O. Another big methane peak. We're up here. Okay. Important, right? And CO2, look at how small that is, a little blip over here. They threw in ethylene just to show you what the infrared looks like. What impression are you supposed to get from this? That methane is more important than CO2. That's the goal of showing this slide. However, remember that little outer blue line, the radiation you would have got if there was no planet, no atmosphere? Well, now we've put in a dashed dot line here what that line is. That's the radiation coming off the Earth. How much of that is over there where methane is so important? How much of it is here? What's this? Formaldehyde, water, okay? When you look at the whole system across the infrared, this, by the way, goes all the way down to 0. The peak is right near CO2. CO2 sits right at the center of that big bulge, the blue line. And the amount of energy being radiated by the Earth is falling off like a rock. And so when you come to another methane peak, you've got about 20 or 30%, about 20% of the peak. So on those three grounds, methane, there isn't very much. 2, water swamps it. And 3, the energy isn't there anyway. Methane doesn't get a piece of the action. They tried to make the ratio of 2 different slopes. Let's add 1 part per million to CO2 and see what happens. Let's add 1 part per million of methane and see what happens. Well, CO2 was way out in the flat part of the curve. Its slope is 0, very close to 0. Methane was just a little dribble at 1.8 parts per million, so increase it by 1 part per million. It's a big deal for methane. Try to form the ratio of those 2 different slopes, and what do you get? Your concentrations of these things, at the time they made the original calculation that was in AR4, CO2 was 385, now it's 410, not much of a difference there. But methane is still down around 1.8. Now, remember this? That's CO2. Methane has a curve that has the same general shape. Methane is going to do all its damage in the first few amounts. So what's your slope? When you're down at the 1 part per million range, over here, that's a real steep slope. When you're out there at 400, that's a very flat slope. Okay? Very flat means very small. Very steep means very large. So now, if this thing will ever advance, here you go. 4th grade arithmetic where you learn how to divide. The quotient is equal to the numerator divided by the denominator. Notice everybody remembers from 4th grade that you can't divide by 0. Well, you can divide by a real tiny number that's close to 0. So, increase by 1 part per million. CO2 barely budges. CH4 changes a lot. So what do you get? Huge numbers. Okay? Remember, the quotient is numerator over denominator. Numerator is a fairly finite number. Denominator is incredibly tiny. Therefore, the quotient is going to be really big. For CH4, you get 28. For nitrous oxide, you get 300 or so, maybe 320. Freons, these odd things that are in air conditioners, over 1,000. Numbers like 1,400. Remember I said they published this big table of numbers to impress you? Well, that's the kind of numbers you get there. Not one of them means a thing. Absolutely meaningless because numerator over denominator blows up when the denominator is tiny. When you got a flat curve and you use that slope as the denominator, you're going to get some big answer no matter what number you put in. So, the real spectrum, the things you saw that Van Weingarten and Happer calculated, that's what's real. That's what you want to believe in. That's good, solid scientific method. That's real physics. That's radiation transfer. That's what's important. I have a thing called famous last words. In the 3rd assessment report, the IPC actually said this. The climate system is a coupled, nonlinear, chaotic system, and therefore, the long-term prediction of future exact climate states is not possible. When you go in there and say, don't tax us, quote that to them. Okay? This whole exercise is practice, it is beginning, it is trying this and that out, but predicting the long term, including the long-term effects of your buying more sheep or cattle, is not possible. And you just have to make that clear to your elected officials, and you gotta get them to pay attention to you. So, with that, the policy implications, same one I showed before, and I say believe Van Weingarten and Haber, because they did the correct scientific approach. They used the scientific method, they got it right, used their results instead of this crazy number with a little teensy denominator that blows up and gives you a silly number. Because the greenhouse gases are not going to stop the climate from changing, therefore, don't take expensive actions to mitigate it, don't strive to reduce CO2, and don't impose new regulations or taxes upon the farmers. This is where you are in the right. You hold the cards, you're the ones who are right about science, you're the ones who deserve to be heard, your voice deserves to be heard in your local governments, parliament, etc. But there is no reason for you to be intimidated by fast-talking guys who don't know the science that underlies the topic. So I thank you very much for your attention, and I hope I can answer questions for you.
Hey, thanks to everyone that turned up tonight, and thanks to Dr. Tom Sheahen. My name's Brian Peterson. I'm the coordinator for Groundswell for the Manawatu Horowhenua in Rangitikei. I'm a local dairy farmer, and I'm working alongside Groundswell because we seem to be the only lobbyist and the only advocate standing up against unworkable government regulations and council regulations on behalf of farmers and rural New Zealand, agricultural business and the Kiwi people. Here is a few statements and questions that Groundswell are pushing towards our politicians that I've prepared today. New Zealand contributes 1/100th of 10% of global methane. 50% of that methane is created naturally. 10% comes from animals. Now, just take this on board, how stupid this whole methane argument is. On the east coast of the North Island is the Hikurangi Trench. It's where the Australian plate and the Pacific plate collide. It starts at Kaikoura and finishes on the Gisborne coast. It's seeping more methane than 50% of all ruminant animals in New Zealand on a daily basis. How does James Shaw and the government plan to plug that?
Stuff them all down there.
Good plan. Good. The IPCC, which is the International Government Panel for Climate Change, stated that they overstated methane's damage by 3 to 4 times in their exaggerated results. So that's 300 to 400% wrong. But still James Shaw and our government want to tax farmers on our emissions. Our New Zealand farmers are leaders in sustainable, emission-efficient production of nutritious dairy, meat and produce. So they don't have much more room to find efficiencies in emissions, leading to reduced production. A 2021 Ag Research study showed that New Zealand dairy farmers have the lowest carbon footprint for milk production in the world. No country comes even close. A 2020 study, University of Auckland, it showed that New Zealand sheep and beef farmers are already very close to being carbon neutral. On the government's own numbers, farming tax will reduce sheep and beef production by 20% and dairy production by 6%, and more farms are converted into pine plantations, leaving already struggling rural communities without their livelihoods. A reduction in production is expected to lead to increased cost of food in New Zealand, which New Zealand households can't afford in the middle of a cost of living crisis. Foreign, less efficient farmers who aren't subject to the farming tax will fill our share of the market potentiality, causing global emissions to increase. The government should be concerned with global warming, not New Zealand warming. New Zealand's government farming tax is disproportionate response to New Zealand representing only 0.017% of the world emissions. Almost half of New Zealand's export income comes from pastoral agriculture. With that revenue at stake, New Zealand's standard of living is under threat from farming tax. New Zealand cannot afford this world-leading experiment of tax, countries with high-emitting farmers should take the lead first. This tax will breach the clause of the Paris Trade Agreement, which states climate change mitigation should not reduce food production. Please start supporting Groundswell in helping us ask the questions to other rural advocacies, the advocacy groups that are not supporting farmers right now. Over there is a donation box for our Farmers Fighting Fund. Please take a sticker for your ute or mailbox as a donation and thanks for the donation. Have we got any questions tonight for Dr. Tom? Yep.
Yeah, Tom, you mentioned about infrared measuring. We've been looking at some imagery out of a company from Europe called EOS, doing a lot of agricultural satellite imagery. How accurate is that imagery that can be used for our gas emissions on say a farm scale?
Well, okay, the satellite data that I showed here, remember the three things on the right side? That's from a satellite. So it's a much bigger view, scale, etc. than a typical farm. If you wanted to use infrared on a farm to inspect something there, put it on a drone, take it up and look down from the drone and scan around all day long as much as you want. And you can see possibly if there's a cluster of cows somewhere, you might be able to see a little extra methane. But of course, my message I just gave you, never mind how much the methane is. It isn't enough to bother with.
So if the water vapour in the air is relatively high, which in our climate it often is, will it still show up on an infrared?
If you're looking at the right wavelengths, yes.
Right.
Yeah. If you're looking in this range of about 8 microns to about 30 microns, you'll definitely see it for sure. Yeah. You definitely can. Yes, please.
If we were to tell a local politician or somebody who was in favour of, getting rid of methane, reducing it, who didn't understand the science we were talking about, what are the critics of what you're telling us say, and how would we answer that? Just go back to what you told us, because there must be, there must be an argument that's counted back towards what you're saying, because what you're saying seems to make sense, but I can't understand why it's not been taken up or followed. Is it because I've come so far with developing those climate indicators that they can't backtrack? Is that the reason? I'm trying to think what argument would put against. Yeah.
The argument almost always falls into the category of ad hominem, means to the man in Latin. There's an old lawyer's slogan that says, if you haven't got the facts, argue the law. If you haven't got the law, argue the facts. If you haven't got either, then attack the man. And all of us, when we give a talk, will be criticized for not being a certified climatologist and things like that. And the fact that people know an awful lot of physics and science, as Van Weingarten and Happer certainly do, goes in one ear and out the other. People have a commitment to a narrative that they want it to be this way, and they will do everything they can to duck the science. And your job in campaigning, lobbying, whatever, in your communities and in your national government is to not let them off the hook with excuses like that. Say, no, you must argue the facts. Is there something wrong with what we said about radiation at the wavelength of 1,000 wave numbers? Is there something wrong with this intensity? So they will be silent. They haven't got the technical acumen to argue effectively against the facts. And that's a real good trump card that you want to play when necessary. But do not listen to sentences that begin, I'm not a scientist, but. Because the next clause is going to be something really dumb. And you've got to be prepared to dismiss their faulty scientific arguments just as fast as they dismiss our star scientists as not climatologists or whatever, you know. I can see some of them saying, well, yeah, I know he's a PhD and he practically won the Nobel Prize, but he didn't go to a university in New Zealand. I mean, the absurdity of the attacks should be embarrassing. So, but that's the kind of responses we get. No one, and these papers by Van Weingarten and Happer have been out for about 4 or 5 years now. No one has attacked their science. Just, they can't do it. Yes, please.
So the CO2 Coalition out of like Arlington, Virginia, how strong are they? Are they doing a lot?
Yes, they're wonderful. That group was founded by Will Happer. The way he founded it was the late founder of my organization, Science and Environmental Policy Project, was the great Fred Singer, one of the all-time great 20th century scientists. Fred Singer gave Happer a prize of something like $10,000 or $20,000, and Happer parlayed that into the formation of the CO2 Coalition, who have done wonderful work in the intervening years. CO2 Coalition has been active for about 5 years, and in that time they have come to dominate the picture. And they even have a committee in which I serve, which is trying to write good material for children in primary grades. And we have a little cartoon, comic book type stuff, but it is done by some really smart people that are very good educators, and they know how to communicate to little children, and they're going to try to remind the children that CO2 is plant food. And it's a shame that 2 generations of their teachers across the world have forgotten that very simple fact.
Yeah, the demonisation of CO2 is illogic.
Mm-hmm. Yeah, that's what it is, demonization.
Quite excited about lifting the CO2 with no negative effect. We'll get a lot better plant growth.
I did wonder about that though. When you said that you could double the CO2 and it wouldn't affect warming numbers, but isn't there, what would the argument be? Wouldn't other side say, well, it's going to have some other effect, it will have something to air quality? I don't know, will it have no effect? You know, it must...
The famous curve that I showed during my talk 3 different times, back here. That's almost totally unknown among the kind of diplomats, bureaucrats, and others who write the summaries of the IPCC reports. The scientists who write the body of the scientific, Working Group 1, the scientific stuff, they know it, and they've said it on page 386 or page 1214. You can't find their stuff if you're going to only skim read it. Those politicians who haven't got time to read are only going to skim read. And that's where you get the mistakes slipping through. Yes, sir.
I think the question that the lady was asking was, as the CO2 concentration goes up, it may not affect the climate, it will increase the photosynthetic level, and however, are there any adverse effects on other things like acid rain, for example, as the carbon dioxide level increases?
If you put one more molecule out there of CO2, some plant's going to come along and eat it instantly. That's where your CO2 goes. It goes into greater vegetation growth. We've seen this with greater tree growth, greater crop growth. All kinds of good things happen from a little more CO2. And that little more could keep going up to a couple of percent. In a submarine, you breathe 8% CO2 in a submarine. This atmosphere could take a lot more CO2, and if there were a lot more CO2, a lot of plants would be very, very happy. And a lot of our productivity would go up. Yes?
So, is the science that you're talking about, and you're telling us the real science, in the States, is it gaining any traction against this climate crisis juggernaut that is, you know, through everything, through the bureaucracy, the politicians, the media, the
Oh, yeah,
universities,
yeah.
everywhere.
CO2 Coalition is being effective at accomplishing things. In America, you can kind of gauge the culture a little bit by the late night shows. The comedians are on late at night on TV. And climate change has become the joke for any excuse, okay? My wife wrecked our cars because of climate change. I broke up with my boyfriend because of climate change. And these jokes are out there, and people just aren't taking climate change seriously anymore because they know the climate does change and you can't stop it. So let it change. It'll be cold next winter, it'll be warm in the summer, etc., etc. Don't try to change the climate. So no, in America anyway, we're definitely got traction. We're going someplace. People are starting to realize that CO2 is plant food, and that chasing the will-o'-the-wisp of trying to reduce CO2 is not going to work. And, well, we're the CO2 Coalition, and we like that outcome. We want people to know better. Yes, please.
Is there any point in discussing the amount of sequestering of carbon in things like grass versus trees? Is it worth discussing that?
No, I don't think so. People are making a lot of money off of promising to plant trees and therefore selling carbon credits, but it is not a meaningful task. It is not an honest business. Because, as I say, you put another molecule of CO2 out there and it's going to be eaten by some tree instantly, and sure enough, our trees are growing better and stronger under slightly more CO2 conditions. Yes?
In New Zealand, at the moment, it's become fashionable to turn away from carbon fuels like coal and turn to alternative wood tissue like wood chip for heating or energy. And one of my mates, and when you get older you start to have people who head up things, he goes throughout New Zealand looking at state-owned boilers. And boilers that were put in 2 years before the Labour Party got in now are being ripped out.
Yeah, right.
And they're putting in wood chip. What do you think of this nonsense that we voted? Is it 1.4 billion already to ripping out boilers that work well, and we've got an abundance of quality coal, while our government imports coal from overseas that's high in sulphur? We've got a lot of thick politicians. And it's like the penny hasn't dropped yet for some of them, because their rhetoric is very much the same.
Your point is very good. I'm aware that a lot of American people who have trees are making big money off of chopping down the trees, chipping them up into wood chips, putting them on a boat and sending them to England, because people over there feel that burning wood chips is better.
There is one group that are selling their wood chip for $900 a cube. And fair
let's
price
see.
could be $400. And we as the people are paying for this nonsense.
$900 per what?
A cubic metre of wood chip. Not even a tonne.
Oh, how much for a ton?
$900 for less than a tonne.
No.
Those figures need published, but they are facts.
You can buy wood chips in America for $240. A ton equals 2,000 pounds, not 1,000 kilograms. T-O-N. Okay?
One of the problems we're facing in what's being stated, there's money in it. So there's money in changing boilers, stripping them out,
Yes.
turning them into scrap,
Right. Yeah.
and
That's the
pulling
broken
down a couple
windows
of
theory.
houses so you can just get storage for the chip.
Yeah.
That's what's happening in some of our schools,
Mhm.
our prisons, our
Yeah.
hospitals,
Yeah.
and we're borrowing heavily, going into debt, and our coal fields are shut down, and our people are struggling, food costs are going up. I want to thank you. Dr. Jock Ellison is a friend of ours in the south. He was an honourable man in his years of serving, And I think it was through Jock that you've come out to the New Zealand.
That is true, yes.
Yeah.
Jock has been my friend for over a decade now, since I first met him in a Las Vegas conference back in 2013. And he's a fine man, a brilliant scientist, and he deserves a lot more recognition than he gets. And we have similar people of high quality in America too, and they also have been denigrated, pushed aside, and mistreated when they, in fact, deserve high recognition. And it's part of the dynamic of the contemporary struggle that is pointed at climate change, but probably has some other underlying reason for it all happening. Oh, no, yes, please.
Yeah, just like that point you made there about climate change and the underlying reason, because I read here it says there's not a climate emergency, which all the greenies would just turn off to, if we said that.
Right.
And like all the science you've got here is very thorough, looks very like convincing. So,
Well, the statement there is no climate emergency is now widespread. Even the scientists who write for the IPCC have said that.
Yep.
And they did it in a complicated way that had to do with scenarios that take too much time to go into it. But they basically said the worst case analysis, which is what the television and newspapers focus on, is absolutely invalid, can never happen, and shouldn't be used at all. And when you only look at the other three cases, called scenarios, you get the answer that there is no climate emergency. And frankly, if there is no climate emergency, why don't we spend all that money on something better? And in America, we see numbers like 500 billion. New Zealand's lucky to have squandered money of only 500 million, you know. But the things they're doing for no other reason than they have the political power to force their way through in America, at least, is just disgraceful. And I very much hope that the community of farmers here can prevent that from happening in New Zealand. Yes?
One more question. With obviously the natural gases like our CO2s and carbon dioxides and nitrous oxides, you obviously explained that really well, but things like nitrogen dioxide, the freons, things like that that are made from industry, are they a greater influence than the natural gases? Or?
Definitely not. Because natural gas is negligible, irrelevant, and so are those even lesser gases. You know, you're talking parts per billion. You think they can seriously affect the atmosphere of an entire planet? No, they can't. There's just not enough. And once again, they are absorbing and emitting radiation in the very same place where water is anyway. So once again, they can't compete. And the Earth isn't radiating where they're active. So they have the same three strikes against them that methane have. So, yeah, you can relax about your leaky automobile air conditioner. It's not an important factor in climate. Yes?
Is that, so for a number of years, you know, in New Zealand we've had this ozone hole above us, and we'll get sunburnt worse than everybody else in the world, apparently.
Yeah.
Is that included in this, or is that a relevant thing?
No. Ozone really is helpful because in the stratosphere it absorbs ultraviolet rays and protects us. The ozone hole is a very interesting phenomenon. When it's winter in the Antarctic, above the air above Antarctica, there are tiny little cirrus clouds form, minuscule little ice particles. And they sit up there and do nothing all through the months of June, July, and August. Okay. Meanwhile, there is chlorine and other gases oozing out of a place called Mount Erebus in Antarctica, which is sort of a stumble bum type of volcano. It's not an important volcano. And if there's man-made freons and so forth, they may circulate all over the globe. Maybe some of those will drift up in the stratosphere too. Okay. Remember, down in Antarctica, you're well below the Antarctic Circle, and so when the sun comes up on September 21st, for the very first time, there is sunlight, photons, energy, which can cause chemicals to combine because of the energy provided by the sunlight. So chemical reactions start to occur, and they are what's called surface chemistry. They can't happen just by molecules banging into each other. It has to get stuck on a surface to hold it in place for an instant so the other molecule can hit it. Surface chemistry is a very special part of the field of chemistry. And that goes on into early October. Well, all this time, your ozone is being eaten up by the surface chemistry. Ozone is getting less, and you have what's called the ozone hole. Then, semi-early October, I'll pick a date, 5th, 10th, 15th of October. It's getting warmer. The sunlight's been active for a while, and these teeny little ice crystals melt. Suddenly there's no surface left. So that chemistry that's important to dispensing with ozone can't happen anymore. So the whole phenomena happens every year between about September 15th and October 15th. And the ozone hole comes and goes. And it's an interesting phenomenon. It is interesting, but it is not harmful to the planet in the long run in any way.
That's still harmful to our schedule.
Cover up.
And does the Northern Hemisphere have a similar?
Yeah, when George H.W. Bush, that is George Bush Sr., was running for re-election, one of the snotty points by the Democrats campaigning against him was that it was all his fault that there was an ozone hole over Kennebunkport. Kennebunkport is a place where George Bush Sr. had a home in Maine, which is one of our most northern eastern states. And this was funny and entertaining in the newspapers, but it had no meaning. But it is true that in the springtime in the northern hemisphere, as in March to early April, there is a gentle ozone hole that also forms, and sure enough, when the ice crystals melt, it goes away. The whole thing lasts about a month. Somebody over here was saying. Yes.
So Tom, you're saying that the relationship between the ozone hole, was only discovered relatively recently, and hydrocarbons is a presupposition?
Well, when you're worried about the hydrofluorocarbons, that's your freons, your refrigerants, and things like that. That is something that is relevant to the ozone hole. Yes, that matters.
So hydrofluorocarbons are relevant to the hole?
Yes.
Right.
Yeah. The surface chemistry that goes forward can take out some ozone. And by the way, the deepest anyone's ever seen an ozone hole is about 50%. So it doesn't dig a big ditch in the ozone, but it digs out some. And as soon as the crystals melt and the sun's shining, the ozone will be back again in no time at all.
All right. Thank you all for coming. I hope you've learned a fair bit off this wealth of knowledge of a man we've got here and we've brought over into the country. He is in association with Jock Allison. Thanks very much for mentioning that. And he's another man that deserves a lot of respect in this country. If you ever hear or see of him talking, make sure you notice and talk about it. Please feel free to take the sheets that you've got on your seats. There's another box of them over by the door if you want to hand them out to your family and friends, or you've got other meetings you can go to spread this word, that'd be good. And remembering in the fact that methane is a gas that's not harmful, and our farmers are going to be taxed on this, according to the government we've got on at the moment. So thanks all for coming. I appreciate you doing that.